So one of the most important quantity that you're going to calculate in particle physics is the so-called decay rate, because the decay rate, gamma as defined by his textbook, is the probability per unit time that any given muon or any given particle for that matter will disintegrate. Because what we really want to know is that how much lifetime a given particle has. And so the interesting thing about our universe is that given a particle, we don't actually have an exact number of when it will decay, because it is probabilistic. So that's why it is written in terms of probability. And so here he was able to derive that the total number, since it will decay, of course, then the total number at any given time dt will decrease. So you have dn, the remaining number of particles after a time dt, will become minus gamma n dt. Okay, so that's the amount that it will decrease after an elapsed dt. Okay, so from there, this is a simple differential equation. You just integrate it, dn over n equals negative gamma dt. You integrate both sides. You find that the solution is actually an exponential. Nt equals n sub 0, where L sub 0 is the original number of particles, e to the minus gamma t. N sub t is the number of particles that remained after a time t. So since their number of lifetimes is different, what we want is the average. And here, Griffiths simply stated that the mean or average lifetime is simply the reciprocal of gamma, the reciprocal of the decay rate. So that's why the decay rate is important. You take its reciprocal, it's supposed to give us the mean lifetime. So he says, as you can check for yourself, so let's do that. Let's check for ourselves. Let me get a clean sheet of paper here. Let's check for ourselves that it indeed is the 1 over gamma is indeed the mean lifetime. So let's write down the number of particles that remains at time t. So it is n of t equals n of 0 e to the minus gamma t. Okay, so I just wrote it down. And so what we're going to do is we would like to ask what is the number of particles that will remain after a time elapsed dt. Okay, so since it will be decreasing, so that will of course be n at some other time t plus dt will be equal to, wow, it feels so awkward to be writing and then looking at your handwriting at the camera. There's like a delay or something. But anyway, so this is just n of 0 e to the minus gamma t plus dt. Okay, of course you can always separate that exponential. That's n sub 0 e to the minus gamma t, and then e to the minus gamma dt. So the thing is, since we know that dt is a small number, it's a small quantity, what we can do here is we can approximate this so that we can expand e about gamma dt. Okay, we take the Taylor expansion of the exponential, and then we discard higher order terms in dt. So what we get is n sub 0 e to the minus gamma t. So you have 1 minus gamma t, and then disregard the higher order terms, right? So you have that equation. So now this is obviously a smaller number than nt because this is at a later time elapse dt. So what we do is we subtract from the original at time t, we subtract the number of particles that will decay at a later time dt. Okay, so we're doing this so that we can obtain the difference, and if we obtain the difference, we compare it from the total amount. That should give us the probability that that particle decayed from a time t up to a time t plus dt. Okay, so this one we subtract by this one, so obviously this first term n sub 0 e minus gamma t will cancel out. What will remain is the second term, and so you're subtracting this with this, so this will become plus, and you get something like n 0 e to the minus gamma t d t. Okay? Alright, so I think I'm missing a, is that right? I'm missing a gamma factor over here. Okay, that looks good so far. So now, this is the total number that decayed between t to t plus dt. So the probability that it will decay between t to t plus dt is just the fraction of that number of particles compared to the total, right? So which is gamma e minus gamma t dt. Okay? So now what do we do? So now we have the probability. So pt, let's call it pt dt, the probability that it decays initially, the initial probability that it decays from t to t plus dt. So what do you do when you have the probability, and then when you multiply the variable that you want to take the average with. So let's say you want to take the average of time, which of course Griffiths called this the tau, the mean lifetime. What do you do is you integrate the probability, okay, that will happen, and then multiply it by the variable that you want to take the mean of, in this case t. Okay, so that's from 0 to infinity. So now we're integrating here. Thankfully gamma is a constant, so that it's a decay rate. So this will give you, let me see, gamma integral from 0 to infinity t e minus gamma t dt. So you can integrate this any way you want, like integration by parts and so on. I think the simplest way is to define gamma t to some other variable u. So that will give you integral from 0 to infinity. Let gamma t equals u, so t will become u over gamma e to the minus u du. But I think you still have there a factor of gamma, right? Because you let u equals gamma t, so t will be u over gamma, du will be gamma dt, or dt is du over gamma. Okay, so the nice thing about that is, of course, one of the gammas will cancel. This will give you 1 over gamma integral from 0 to infinity of u e to the minus u du. Okay, so now this is now a simple integral. You can evaluate it if you want, but the thing is, this is actually a gamma function, because a gamma function, not this gamma, this is a constant, this is a decay rate gamma. The gamma function is defined as some variable, let's say x, integral from 0 to infinity x to the n minus 1 e to the minus x dx, right? And that is equal to the gamma function, which for integer values of n can be evaluated as the factorial. Gamma n is n minus 1 factorial. So in this case, your n minus 1 exponent here, to give you the number, the variable u, is you let n equals 2. So this is just gamma 2, which is of course 1. Okay, so this whole integral here is 1, and voila. Okay, and now you get the, and of course so it ended right where the paper ended as well, so that's very cool. So that is the mean lifetime, since this is 1, is now 1 over gamma, right? Just like what Griffiths wanted us to show. Okay, so yeah, so it's really straightforward, but you know what's hard is writing, like, and then viewing it over the lens of a camera. But yeah, so I'm just trying out if I can like take a video of solutions like this. So I may be doing this a lot in the future if it turns out to be good. All right.